Hello and welcome back. The next topic in Chapter 6 in Klein Organic Chemistry is entropy. So remember, we're trying to define all of the terms in our free energy equation, which is delta G is equal to delta H minus T delta S, where delta G is free energy, delta H is enthalpy, which we've already discussed, T is temperature, and delta S is entropy. So this term, so we've discussed delta H, so now we're discussing entropy. So entropy is a measure of randomness or disorder in a system. So exothermic and endothermic reactions can occur spontaneously, okay, but most reactions are exothermic. So again, we're going to get to delta G a little later on, but if delta G is negative, a reaction will occur spontaneously, and if it's positive, it's going to be non-spontaneous. So most of the time, our enthalpy term is larger than the entropy term, so our delta H term in this equation is going to be larger than the T delta S term, because entropy is usually a very small number compared to the enthalpy term, okay? So if our reaction is exothermic, or delta H is negative, then our delta G will usually be negative. But occasionally we get a competition there, and so we need to understand what entropy is and how it relates to our equation. So recall that entropy from general chemistry can be described as molecular disorder, randomness, or degrees of freedom. It's actually the number of vibrational, rotational, and translational states, or degrees of freedom, in the molecule. Okay? So consider a gas that is isolated on one side of a container, and on the other side of the container we have just, say, a vacuum. If we open a stopcock between those two sides of the container, okay, then the molecules are going to spread across the container from one side to the other, and they're going to evenly distribute themselves across the container. And this is an increase in entropy, or an increase in randomness. So if we have more volume to occupy for that gas to occupy, we have greater entropy. So the total entropy in a system essentially is what determines whether a process will be spontaneous. If the total entropy, or the entropy for the system plus the surroundings, is positive, then that means that the total system and surroundings are gaining entropy, okay? Then a process will be spontaneous. But even if the entropy for the system is negative and the surroundings is positive, as long as the surroundings are gaining more entropy than the system, then you're going to have a positive entropy, okay? But for chemical reactions, we can't really measure the entropy change in the surroundings. We can only measure the change as it is related to the system, okay? So we have kind of a problem, and so what we do is we measure everything in relation to the system, and so we'll get back to that in just a moment. So for that delta S system term, that's the main thing that we can consider as far as entropy of the system. We have basically a couple of different ways that we can increase entropy in the system. So we can go from 1 mole of reactant to 2 moles of product, and that's going to be an increase in entropy. Or we can have a cyclic compound that becomes a cyclic, okay? So we can have a ring opening type of situation. And those both will give us an increase in entropy, which is going to be a positive delta S, which will be favorable for our reaction. Okay, so we'll look at some different examples of that in just a minute. But again, coming back to what I was saying earlier, we want our total entropy for our system plus the surroundings to be positive. Okay, but we can't measure the entropy for the surroundings. We can only in chemistry measure everything as it relates to the system. So what we can do is actually put the delta S for the surroundings in terms of the system. So we don't go through that derivation in this class, but if you're interested, you can look into that further from some other resources. But we can define delta S for the surroundings as negative delta H for the system, so enthalpy, divided by temperature. Okay, so if we do that, we can say the total delta S is equal to negative delta H for the system divided by T plus delta S for the system. And then if we rearrange that equation and do some plugging in, we get our final equation, which is equal to delta G is equal to delta H minus T delta S. Again, your book doesn't go into the actual derivation of that equation, but if you're interested, you can look into that with some outside resources. So what this does is gives us all of these terms. We have free energy on the left, okay, is equal to the enthalpy minus the temperature times the entropy of the system. Okay. So we know that the enthalpy we can calculate because that is the bonds broken minus bonds formed. That's the delta H that we just talked about in the last video. The temperature is going to be dependent on whatever temperature we have that system at. Okay, so we can measure the temperature, or we can adjust the temperature. We can heat it, or we can cool it. We can do something to the temperature to change that as a factor. Okay, and then the entropy of the system is something we could maybe look up in some tables. Now, we're not going to actually do this calculation in this course, but what we do is just get or we may do some simple ones if we're given all the numbers, but what we do is just get kind of an intuitive feel for how increasing one term or decreasing one term affects the delta G for that reaction. So if delta G is negative, then our reaction will be spontaneous and it will occur. So if it's positive, then our reaction doesn't occur. So the reaction is going to favor the reactants instead of the products. Okay, so if it's negative, we favor products. If it's positive, we favor reactants. So for each of the following processes, let's try to predict the sign of delta S for the reaction. So we're just talking about the entropy for the system, so the entropy for the chemical system at hand. In other words, will delta S for the system be positive or negative? So a positive delta S is an increase in entropy, and that's what we want. Notice up here in this equation, if we have a positive delta S, then our T delta S term becomes negative because there's a negative out here, and that's going to increase the negative of our delta G. Okay, so it's going to make our delta G more negative. So we want a positive delta S. That would be favorable. Okay. So what about A? We're going from 2 moles of reactants to 1 mole of product, and so that's going to be a negative delta S. Okay, negative delta S because we're losing entropy. Our entropy is going down. For B, we've got an open ring going to a closed ring. This is a kind of a pericyclic reaction. A was a electrocyclic reaction also that we're going to see in chapter 16 or 17. I think it's chapter 16 in version 3. So for B, we have a ring closure, and so that's also going to be a negative delta S, so we're losing entropy. For C, we've got 1 molecule going to 2 molecules, and so that's going to be a positive delta S. And D is 1 molecule going to 2, so again, that's a positive delta S. For E, we've got this. Sometimes we write some of our reactants over the arrow. Okay, so this is like saying this carbocation plus water yields this thing here. Okay, so we've got 2 species going to 1 species, so we're losing entropy, so that's going to be a negative delta S. And then F is a ring opening, so that's going to be more entropy, and so that's going to be a positive delta S. Okay? And that brings us to the next topic, which is delta G. Like we've been talking about, we're moving toward understanding whether a reaction is favorable or not, and delta G will help us determine that. Okay, so we'll talk about that in the next video.